Welcome to another module in this massive open online course on estimation for wireless communication systems. So what we are seeing currently is we are seeing an example of an OFDM system with n equal to 4 subcarriers. So we have an n equal to 4 subcarrier example of OFDM. Alright, we considered the 4 symbols loaded onto the subcarriers to be 1 plus j, x1, x0 equals 1 plus j, x1 equals 1 minus j, x2 equals 1 plus 2j, and x3 equals 2 minus j. These are the n equal to 4 symbols loaded onto the subcarriers. N equal to 4 symbols loaded onto the subcarriers. Further, what we do is to generate the samples. From this we generate the samples. How do we generate the samples? By taking the samples are generated by considering the n equal to 4 point IFFT. Samples are generated four point IFFT, where the kth sample xk equals summation L equal to 0 to n minus 1 over n xl e power j 2 pi kl divided by n. And we have seen that the samples are given as x0, x1, x2, x3, and the samples are basically your 5 by 4 plus 1 by 4 j, comma minus half j, comma minus 1 by 4 plus 5 by 4 j comma 0. And what we had did later in the next step was to take this and prefix it in before. This is termed the cyclic prefix. This is your cyclic prefix. So this is the block of 5 samples with cyclic prefix. This is the block with cyclic prefix. This is transmitted across the channel, across our 2 tap ISI channel. L equal to 2 tap intersymbol interference channel. And after FFT at the receiver, remember at the receiver we perform the FFT. After the FFT at the receiver, the received symbol pilot output across the Lth subcarrier is given as YL, which is the pilot output across the Lth subcarrier. YL equals HL times XL plus VL. What is this? This is the pilot output across the Lth subcarrier. This is the pilot output across the Lth subcarrier. Now, how to generate these pilot outputs? That is, let us say we have consider the received samples. Remember, we have the received samples. So let us say the received samples are y0 equals, well, 1, y1 equals half, y2 equals half and y3 equals 1. Let us say we are considering this simple example of the received samples. Then what do we do? Basically we take the 4-point FFT, that is n equal to 4-point FFT to generate the output samples on the various subcarriers. The output samples on the various subcarriers are basically generated. So, basically we have the time domain samples small y0, small y1, small y2, small y3, alright. There is a n output time domain samples. We take the n point FFT to generate the corresponding frequency domain samples or the output symbols corresponding to the various subcarriers. Okay. So, we have y0, y1, y2, y3, you take n equal to 4-point FFT and generate across the subcarriers capital Y0, capital Y1, capital Y2, capital Y3, which are the output symbols across the subcarriers. Therefore, for the nth subcarrier, that is given basically by the nth FFT output, that is equal to summation of the time domain samples k equal to 0 to n minus 1 small x k e raised to minus j 2 pi k l divided by n. Now, we substitute n equal to 4, sorry, this has to be n minus 1. Substitute n equal to 4, therefore, this becomes, this is equal to summation k equal to 0 to 3 x k e raised to minus j 2 pi k l by 4, which means basically your y l is equal to summation k equal to 0 to 3 x k e raised to minus j pi by 2 k l. Okay, that is what we have. Okay, so basically the output symbols are generated by the corresponding n point FFT of the output samples. All right. So now let us compute the output symbols y0. y0 is fairly straightforward, that is I substitute L equal to 0 above xk e power minus j pi by 2 k times 0. So, basically this quantity is 1 and that is very simple. So, basically k equal to, simply k equal to 0, the summation of the various time domain samples, which is equal to basically 1 plus half plus half plus 1, which is equal to 3. So, basically my y0 is equal to 3. Let us compute y1. y1 equals summation k equal to 0 to 3 yk e raised to minus j pi by 2 k times 1, which is basically k itself. So, this is summation k equal to 0 to 3 yk e raised to minus j pi by 2 k, and now expanding this summation, that is basically small x 0, I have small x 0 plus small x 1 e raised to minus j pi by 2 plus small x 2 e raised to minus j pi plus small x 3 e raised to minus j 3 pi over 2. Now, substituting the values of the time domain samples, I have 1 plus half times minus j plus half times minus 1 plus 1 times j, and you can check this is basically 1 minus half j minus half plus j equals basically half plus half j. So, this is basically what is this? This is the this is y1, that is a symbol received across the output symbol across the first subcarrier. Remember, y1 is output symbol across subcarrier L equal to 1. Output symbol across the subcarrier L is equal to 1. Okay. Similarly, one can compute the output symbol across the subcarrier L is equal to 2, that is summation k equal to 0 to 3 yk e raised to minus j pi by 2 minus j pi by 2, substitute L equal to 2. So, this is summation k equal to 0 to 3 yk e raised to minus j pi k, or basically k pi, which is basically I am sorry, I think I have been made a small mistake here. I think this has to be the samples y0, y2, y1, and this is of course y3, that is the samples small y's. I think I have made, I think all of these small x's should be replaced by the small y's. These are the corresponding samples. So, this is also has to be replaced by small y's, because the output sample y of L corresponding to subcarrier L is given basically by the FFT of the output samples, time domain samples, which are the small y's. Okay. All right. So, basically just to correct these things, that is replacing the small x's by the small y's, what I have is, I think this is yk, this is y0 plus y1 e raised to minus j pi plus y2 e raised to minus j2 pi plus y3 e raised to minus j3 pi, which is equal to 1 plus half into minus 1 plus half into 1 plus 1 into minus 1, and now you can see all these cancel. I have a 1, I have a minus 1, I have minus half, I have a half. So, this basically equal to 0. So, what I have is y2 is equal to 0. Further, y3, that is output symbol corresponding to subcarrier 3, is equal to summation k equal to 0 to 3 y of k e raised to minus j pi by 2 times 3k, which is basically k equal to 0 to 3 yk e raised to minus 3 pi by 2 j 3 pi by 2 k, which is basically, if you look at this, this is equal to y0 plus y1 e raised to minus j 3 pi by 2 plus y2 e raised to minus j 3 pi plus y3 e raised to minus j 9 pi by 2, which is equal to 1 plus half times j plus half times minus 1 plus 1 times minus j, which is basically equal to half minus half j. And just to check if we have any typographical errors above, just to carefully check once more, that is basically replacing all the small x's by the small y's, which are the time domain output samples. Okay. So, these are basically the small y's, just to clarify it once again, because there seems to be some confusion. These are the time domain output samples. And the small x's are the time domain input samples. These small x's, these are the time domain input samples. So, I hope that aspect is clear. So, these are the time domain input samples. That is, when we say the time domain input samples, these are the samples which are transmitted over the channel, and the time domain output samples are corresponding output samples which are basically received over the channel. Alright. So, this is the difference between the time domain input samples and the time domain output samples. Alright. So, now basically we have found the time corresponding frequency domain output symbols, the capital Y0, capital Y1, capital Y2, capital Y3, and therefore, the frequency domain output vector comprising of symbols received across the subcarriers is basically Y bar equals Y0, Y1, Y2, Y3, and this is basically equal to 3. We just write it down clearly. This is basically equal to 3 half plus half j 0 half minus half j. Now, let us form the pilot matrix or pilot matrix X. This is our pilot matrix. Remember, this is a diagonal matrix in the case of OFDM. This is equal to, remember, this is equal to X. This is your diagonal matrix X0, X1, X2, X3, 0, 0, 0, 0, 0, 0. Remember this, what is this? This is a diagonal matrix. This is a diagonal matrix. Now, I am going to substitute the symbols loaded onto the subcarriers. These are 1 plus j, 1 minus j, 1 plus 2j, 2 minus j, okay. And therefore, now the least squares estimate of the channel coefficients across the subcarriers, that is the capital H's, are given by basically the pilot matrix X inverse times Y, right. We said that we derived that formally, that because X is a diagonal matrix which is invertible, this is simply the inverse of X inverse times Y. So, therefore, H hat equals X inverse times Y, and X is a diagonal matrix. So, the inverse is simply the inverse of each of the diagonal elements, that is the reciprocal of each of the diagonal elements, 1 over 1 plus j, 1 over 1 minus j, 1 over 1 plus 2j, 1 over 2 minus j, which is basically multiplied with your output vector containing the symbols received across the subcarriers, that is Y bar. So, this is X bar, this is diagonal matrix X, this has to be capital Y bar, this is 3 half plus half j, 0 half minus half j, which is basically, now again it is fairly simple to simplify this at this point. This is 1 minus j divided by 2, 1 plus j divided by 2, these are the diagonal elements I am writing, the rest of the elements are 0 anyway, 1 minus 2j divided by 5, 2 plus j divided by 5, 0, 0, 0, 0, 0 0 0 0 0 0 0 times 3 half plus half j 0 half minus half j, and you can multiply this out now and you can clearly see that basically your h hat, which are basically your vector, a vector of channel coefficients across the subcarriers, right, estimates of the channel coefficients across the subcarriers rather. This is equal to, well, one multiplying 3 by 2 minus 3 by 2 j and half j, and this is 0 and this is 3 by 10 minus 1 by 10 times j, all right. So, h hat denotes the vector of basically estimates of the channel coefficients across the various subcarriers, all right. H hat 0 is the estimate of the channel coefficient capital H hat 0 across subcarrier 0, H hat 1 across subcarrier 1, so on and so forth up to H hat 3, all right. So, basically we have H hat vector of estimates of subcarrier coefficients. For instance, h hat of L equals basically your estimate of the coefficient across subcarrier L. Estimate of coefficient across subcarrier L, all right. So, now we have found the estimates of the coefficients across the various subcarriers, that is h hat 0, h hat 1, h hat 2, h hat 3, that is the capital H's, right. From this we can also compute the estimates of the channel taps, remember the small h's, h0 and h1, and remember to do that what we said is basically, if you remember again, what we said is basically h 0 comma h1, if you look at this 0 padded, and if you take the n equal to 4 point FFT, you generate the coefficients across the subcarriers, isn't it. So, you have h0, h1, h2, h3, and these are the channel taps. And these are the channel taps. Now, if you take the IFFT, now what we have is something slightly different. Instead of this, what we have is we have the estimates of this, right. These are the, we have the estimates. So, naturally, if you take the IFFT of the channel coefficients, you get back the channel taps. However, what we have are the estimates of the channel coefficients, h hat 0, h hat 1, h hat 2, h hat 3, and now once you take the FFT, that is n equal to 4 point FFT, what you get here are basically estimates of the channel taps or estimate of channel taps in time domain. These are the estimates of the channel coefficients in frequency domain, yeah, that is important to keep in mind. Estimate of channel coefficients these are the estimates of the channel coefficients in the frequency domain, and that is something that is important to keep in mind. From that you take the FFT, you get the estimate of the channel coefficients, I am sorry, you take the IFFT or the IDFT, because from the frequency you have to go to time. So, you take the IFFT or IDFT and you get the estimates of the channel taps in the time domain. So, basically what you have is h hat 0 equals 1 over n 1 over n summation L equal to 0 to 3 h of L e power j 2 pi. Now, k, this corresponds to k equal to 0. So, substituting 0 into 0 times L divided by n, of course, this is 1. So, again substituting n equal to 4. What this is simply this is the sum of the, of course, I have to have the estimate, sum of the estimates of the channel taps H1 H hat 1 plus H hat 2 plus H hat 3, which is basically equal to, now you substitute the estimates of the channel coefficients across the subcarriers computed above. So, this is 3 by 2 minus 3 by 2 j plus half j plus 0 plus half j, indeed plus half j plus 0 plus 3 by 10 minus j by 10, which is equal to, if you look at this, 1 over 4, this is equal to, well, this is equal to 1 over 4 18 by 10 minus 11 by 10 j, which is basically h hat 0. Therefore, you can say h hat 0 equals 18 by 40 minus 11 by 40 j. I think this is the estimate of channel tap H 0. This is what is h hat 0, this is estimate of channel tap H 0, and by the same token, how will we compute H hat 1, which is the estimate of channel tap? This corresponds to estimate of channel tap H 1 corresponding to k equal to 1, that is basically your summation L equal to 0 to 3 h hat of L e raised to well, the IFFT. So, e raised to j 2 pi, you have to substitute k equal to 1 times L divided by 4, which is summation L equal to 0 to 3 h hat L e raised to j pi by 2 L, which is equal to, well, this is equal to, substitute the various quantities, what you have is basically 1 over 4 3 by 2 minus 3 by 2 j times 1 plus half j times j plus, of course, there is 0 plus 3 by 10 minus 1 by 10 j times minus j, and you go with the summation, and what you will find is basically you have here 1 by 4 9 by 10 minus 18 by 10 j, which is equal to 9 by 40 minus 18 by 40 j, and this is h hat 1. This is the estimate of the channel coefficient across the, what is this? This is basically your estimate of the channel coefficient across the estimate of channel coefficient. In fact, it is not a channel coefficient, it is the time domain channel tap. It is the time domain channel tap estimate of H1 or channel tap H1. So, basically this is the estimate of channel tap H1, this is the estimate of channel tap H0. So, we have H hat 0, we have H hat 1, and that basically gives us the estimates of the various channel taps. So, that is what we have done. In fact, if you look at this example, what we have done over this module and the previous module, we have comprehensively looked at this OFDM estimation scenario in a very thorough fashion, and it is basically a sequence of a large number of steps, and one should remember the logical ordering of these steps. Basically, you have the symbols that are loaded on the subcarriers in the frequency domain, you convert it into the time domain by taking the IFFT of the symbols loaded into the subcarriers, add the cyclic prefix, transmit them. You receive the output samples in the time domain, which are the small y's, you take the FFT of these output samples, you generate the capital Y's, which are the frequency domain symbols that are received across the various subcarriers, right. You have the frequency domain symbol outputs, you have the frequency domain symbols loaded onto the subcarriers, alright. Now you get the channel coefficients, the estimates of the channel coefficients in the frequency domain, that is the FFT domain. You perform the IFFT of this and then you get the estimates of the channel taps in the time domain, alright. So, that is basically, once you understand OFDM, I think that sequence of steps is fairly logical and also to a certain extent intuitive, alright. And this example again clarifies in a step by step fashion how to go about channel estimation in an OFDM system, albeit in a simple OFDM system with 2 tap ISI channel, that is an intersymbol interference channel with 2 channel taps and number of subcarriers n equal to 4, because of the limitations of the scope of this class we cannot do an elaborate system with a large number of subcarriers and a large number of channel taps, although from this example I think it is fairly clear to everyone who has followed it that this can be very readily generalized to a system with a large number of subcarriers and of course a larger number of channel taps, and that can be implemented very efficiently using software that is available or by coding it appropriately to simulate it, alright. So, basically this concludes this simple OFDM example, and I urge you to go through again this example to understand the working of the OFDM system as well as the channel estimation process better, alright. We will conclude this model here. Thank you.